Hi everyone, welcome back. And today I'll be doing this question called sliding window maximum. And this will be part of a new series that I want to try. This is a collection of the Blind Scientify Neat Code 100, that sort of collection list that I found on Reddit. And I'm just trying to keep this Excel sheet to keep track of the progress. So let's get straight to it. So you're given an array of integers, and there's a sliding window of size k, which is moving from left to right, and you can only see the k numbers in the window, and each time the sliding window moves right by one position. So effectively, it's a standard sliding window. It'll see the items in three by three. So the first three, then slide by one, another three, slide by one, another three. And every time you slide, you want to return the max of the sliding window, of the slide of the objects inside the sliding window. So this seems like a very straightforward, seems simple to understand, but it is harder to execute given the constraints. So let's just implement the pseudocode for the Python code for the brute force method. So that's easier to understand as well. So firstly, I would have to have a finale array, like a final output thingy. And I will create a for loop for the sliding window for I in range len nums minus k plus one. And I'll create a new array at the bottom, which is I and I plus k. And at the end of it, I will append the max of the new array that I created into the final array, and I'll just return the fin variable. And this logically should be correct. So it passes the test case. And if I run all the other test cases, if I submit for this thing, I will hit a time limit error. And that's mainly because this is the brute force method and it's very inefficient. So in terms of time complexity, this will be n time complexity for the for loop and another n time complexity for the maximum operation. To find the maximum, it will traverse through everything and find the maximum item. So a combination of this is n times n squared. So it's n squared time complexity, and hence it hits the time limit exceeded. And that is not right. So what is the solution? There's many ways to solve this, but my preferred method is to use this thing called a heap queue or a heap solution. So heap queue is the module that Python has to make it easier for us to implement the heap queue, to implement the heap. And a heap is effectively a tree-based data structure that has some benefits, and I will explain the benefits shortly. So in a heap, insertion and deletion is log n time complexity. Whereas for and another thing is accessing the minimum most or the more maximum, depending on how the heap is organized, is constant time complexity. So the problem over here is that at each sliding window, I'm implementing the max array every single time. And since k can be as big as the entire as big as the entire input array, the max array is massive. So max running on that is really time consuming. But if I were to access it in a min heap or a max heap, the accessing the extreme point, the maximum or the minimum, is just a constant time complexity. And that is the benefit. So I'll insert something and I'll just access the topmost item. And it trims significantly the time complexity that it will take to solve this. So how does it actually play into this picture? So what I'm hoping to do is for the first three things, I'll just add it to the heap queue. I'll just build the heap structure. In Python, another thing, by the way, the heap queue module by default implements the min heap to build the max heap because we want to access the max in the most efficient way. We don't want to access the minimum in the most efficient way. All we need to do is just invert the plus and minus. So all the pluses will become negative. So the -3 will become the smallest item, and by effect, it will become the root node. And all we need to do is just take the root node and just flip the negative sign, and it just works fine for us. And this is a very common way to handle heap queue solutions. Okay, I'll go straight to implementing this. Okay, I will go straight to explaining what needs to be done. So for the first three things, we will just add it to the heap queue. And when we add it to the heap queue, we will just get like three will become the -3 will become the root node. Um -3. Yeah. -3 will become the root node, and it will have -1 and 1 like this, and so on and so forth. It'll go like, it'll keep like this. And then when I'm traversing to the next one, I want to add the -3 again. And -3, when I flip it, it becomes 3. So it will not go to the top, it will go to the bottom somewhere here. And when I go to the next one, 5 is the biggest item. So -5 will go to the top. So it will replace this, and -5 will become the root node. So accessing the root node will give us -5, and that's the one that needs to be appended to the next one. And if I keep going like this, 6 will become the root node at some point, and then 7 will become the root node at some point, and anything smaller than these will go to somewhere in the bottom, and we don't need to worry about them for now. Because in this example that they've given, it's quite straightforward, whereby the next biggest item is like, just nice, it happens to be that the biggest item in the array is also within the search scope of this thing. But there can be a situation whereby it is not the case. So let me just write the test cases, the two test cases that I'm thinking of. So one test case is the one that they've given. If it's this and k is 3. Another test case is, what if the maximum has been seen in the past and now we are required to work with the same approach that we described just now? So in the initial question, in the initial test case given, this is what they give. And this is quite straightforward. The first 3 is 3, the next 3 is also 3, the next 3 is 5, and the next 3 is 5, and the next 3 is 6, and the next 3 is 7. So perfect, no problem. But if we do that here, the first 3 is 7. Okay, correct. The next 3 is also 7. Correct. I'll be adding, so in the first 3, I'll just add it to the heap queue, and all good. It'll just form the tree nicely. The minimum most value will be the top. I'll add 1. 1 won't become the root node, so nothing to worry about. 7 will still be the root node. I'll add 3. And 7 will still be the root node, and 7 is still within the scope that we're looking at. So all good. We can just keep adding it to the list. Now here comes the challenge. I now add -1 to the heap queue. I'll add -1 to the min heap. And the minimum most value, which is 7, hasn't changed. It'll still be the maximum value. And by the logic that we implemented just now, 7 is what it will return. But 7, the index for 7 is not within the sliding window scope. And therefore, this is the wrong answer. Like, we basically should have returned 3. So we need to find a way to implement an algo such that if we add the -1 into the heap, and we check for the maximum node, which is the root node, and if the root node's index is outside this zone, we need to remove that. And the good thing about a heap queue is removing the root node is also log n time complexity. So it doesn't explode the time complexity in any way. So we'll add this -1, we'll add -1 log n, and then we will have to remove, like, we will search for 7, which is constant time complexity. We'll search for the root node, which is 7, and 7's index outside this zone that we're looking for, and hence we will remove 7. After we remove 7, it will auto adjust such that 6 becomes the root node now, and 6 is still not within the zone of these 3 indexes, so we will need to remove 6 as well. And then we'll be left with -3 at the top for the minimum most node, which could be the correct answer, but only depends, because there could be a case whereby this 3 is at the top node, and we have to see if that index is within this zone. If it's not within this zone, we will pop that as well. So we'll pop this, and we'll be left with this three being the root node, and these two being in the side. And at that point, when we access the minimum most node, it will be within the sliding windows scope, and hence that is the correct answer, and we can continue. Next one will be 3, 1, -3. We'll add -3 to the heap queue. -3 is much smaller, so it will go somewhere on the bottom. And when we access the rootmost node, it will still be 3. So it'll be 3. And after that, we will go to these three things. We will add 5 to the mix. So 5 will come in. And at that point, 5 will be the maximum most node. And hence, when accessing the root node, it will be 5. And that's the correct answer, because 5 is still within the search zone of these three things. So this is the long-winded explanation of what we are trying to achieve. Now I will write the code and explain again if it makes it clearer. Feel free to speed up and slow down as required. So to implement a heap queue in Python, it's relatively straightforward. They make it quite simple for us as well. So it's the basic data structure for it is just the simple list array that we have over here. And we will have this output array. This is the one that we will return at the end of the day. And I will build a for loop such that I will have a chance to append. I will be heap pushing everything into the heap queue. So this is how we do it. For I in range len nums, I need to push everything now. So heap queue dot heap push, make a reference to the heap, and then give it the object that we want to push. So I want to push both the value, which is nums I, and I put a negative because I want to flip it, because by default heap queue is a min heap. And to make it into a max heap, we just need to flip the negative signs. And this is a very common practice of how they do it. So I'll be basically heap pushing a tuple, which is nums I, negative nums I and I index. It'll first look at this to sort. So it'll sort it by this first, and then it'll sort by the index. Okay, so minimum most item will be at the top. Heap queue dot heap push. So by doing so, we will be pushing everything, and the rootmost node will just be heap 0. That will be the rootmost node, but we'll get to that later. Now, if I is greater than equal to k minus 1, the reason why we do this is because below in this step, we are going to do the validation such that is the root node within the search scope of the sliding window. That's what we're going to check now. And we don't have that check. That check is not necessary if the I is lesser than k. If it's lesser than k, we just need to push it in, and we can just need to continue. We don't need to think so much. So and this is the continuous check just now. Like just now when we checked 7 in this scenario, 7 was the peak node, and 7 is not within the scope. So we pop it. But even after we popped it, 6 became the root node, and 6 is not within the search scope. So we need to pop that as well. So we need a sort of a conditional while loop such that it will keep checking if the root node is within the search scope of the sliding window. And that's what we'll do here. So heap 0 gives us the rootmost node, and index 1 of the tuple will give us this index. So is the index of the root node lesser than equal to I minus k? I minus k will bring us to, like for instance, in this example, it'll bring us to somewhere here. It'll say like, is it lesser than this? In this case, 7 is lesser than this, and hence it will be ejected. So if it's lesser than this, we eject it. Heap queue dot heap pop. So heap pop will remove the top item, which is the rootmost node, which is 7 in this case. And yep. Then after we pop it sufficiently, we will be confident that the root node that we have right now is the biggest item, and it is the one that needs to be appended to the final output. So output dot append heap 0, and we need to return the value, not the we need to return the value, not the index. So heap 0 will return the tuple and heap 0, 0 will return the item. And we will just need to flip the negative sign so that it's an accurate value. And now we can just return output and it should be all good. Okay, so I'll just comment out all these things and let's submit. Okay, so it passes the test cases, and there are other methods to do this as well, using like dynamic programming or everything. But this is something that I personally like this version of the solution using the heap queue solution. And in terms of time complexity, this operation will be n time complexity, and the heap push will be log n, and the heap pop will be another log n, and appending will be constant. So it'll be n times log n effectively. So let's just write it here. Time complexity n log n space will be n, because we are recreating at the worst case scenario, we might be recreating like uh as in not a worst case scenario, it's just n, because we would have to create a new output array of um length nums minus k. So it's just n. It's a linear space complexity. So yeah, there you have it. And let me know if you have any questions. I know this explanation might be a bit confusing. Feel free to rewind and watch, or like ask me any questions that you feel like in the comment section, and I'll try my best to answer them. And that's it, I guess. And I'll see you guys when I'm attempting the other solutions over here. And hopefully I can complete this as a successful series as well. So yeah, see you guys in the next video and cheers. Bye.